So this is a video tutorial about DDSimka web application. And before we start, two very important messages. First of all, if it's your first MDA Tools application, web application that you use, please start watching video tutorials for PCA and preprocessing because they cover also the most essential parts relevant to all applications. For example, PCA explains how to prepare your data set. It explains how to use preprocessing. It explains how to use sessions. It explains how to use this app offline and so on and so forth. And preprocessing explains how to apply preprocessing because preprocessing is a part of all apps here. After you've done that, or if you already have done that, let's take the DDSimka application. So I open the app. And the second important message is that this app is actually described in our tutorial about DDSimka, which we published in 2024 in Journal of Chemometrics. And this tutorial covers both the theory, but also it covers, gives a description of this app, web application, with some practical examples. And I must say that this is a new version of this app where we redesigned this application based on the user feedback. And therefore, it will look a little bit different. For example, these three tabs that we have here, train, test, and predict, they are more conventional tabs to any chemometric modeling. You first train your model, then you test it, and then you use it for predictions, right? In this app, it has a little bit different structure. However, all functionality is kept. So it means that you can reproduce all these examples in the new application. And this is what I'm going also to do in this video tutorial. The tutorial is built as follows. First of all, I will explain functionality of every tab in separate videos. So this video will be about training model. Next video will be about testing, and then how to predict how to make new predictions. So let's start with training the model. Okay. So we are going to use dataset Oregano, which is also explained here in this tutorial. So I will download this dataset. And then I switch to the Finder and open it. So you can see inside there are several files. First of all, you can see target train and target test. Target train, you can see inside, what is inside, consists of the training set. And now you see that it's very important, if you train your model, it's very important to provide your data as a CSV file where there is a column with classes. For example, in my case, you can see I have column with labels for every row, so unique object labels. I have column with classes, and then I have these predictors, right? These are the spectra in this case. You can also see that I have wave numbers as a header, as a variable names. This will be needed when you load the data. But the most important thing is this one. You need to have the class label for training and for testing your model in your data. So that's the most important. We also have some other data sets. You can see target test. You can see some others. I will cover them later in this video. So let's open the training set. Good. Now you can see that the app automatically recognized what is delimiter. Do I have row labels or not? Do I have header or not? And it also recognized that header consists of values, not text labels, right? I can also add these wave numbers here. It's not important. It's only needed for the loadings and for some other plots, but most of the plots actually do not require this. But let me do it anyway. Okay. Then preprocessing. Preprocessing is very well covered in PCA app videos and preprocessing web videos. In this case, the data is already preprocessed, so I will skip the preprocessing. Now the next step is to create a global PCA model, which will be a core for my Simka model, for DDSimka model. And I will just use the default settings. I don't need to scale my data. I don't need to standardize it. I will just min center it and use 20 components as the max. Okay. Next step is to generate a validation set. Although it looks like it's a cross validation, it's not. It's what is called Procrustes cross validation. It's our method that we proposed recently. The idea is that we use cross validation to generate a validation set, and then we use this generated set as just as a normal validation set. So in this case, because my data set is relatively large, I will use 4 Venetian blinds with 4 segments. Okay, that's it. So this actually widget, it's settings of your Simka models. As you can see, you can change the number of components. You can change alpha. It's a chance for getting a false negative. So it means that, for example, if you use alpha 5%, your expected sensitivity will be 95%. Here it will be 99 and so on. Okay. Gamma is needed to detect outliers. We will discuss it in a minute, as well as robust limits. So robust limits, we need them to detect outliers. Here you can see the main plot. It's acceptance plot. You can see it also here. And then you can see you can make acceptance plot for two outcomes, right? It's a calibration set and this validation set. You can see it's PV Procrustes validation set, okay? Sometimes it also makes sense to do the log transform for the access and for the values and also show labels like here, okay? Well, as you can see, there are two limits here. This limit is a decision boundary. It is used to make a decision if it's classified as a member or as a stranger. And this limit is for outliers detection. As you can see in my current configuration, 3 components. I don't know yet how many components to use. 3 components, 5% alpha, 1% gamma, classic limits. I have most of the objects considered as members, and they are regular here. 3 objects are considered as extreme, so therefore they are outside of the class, so they are false negatives. And you can see none of the objects are considered as outliers. On the other hand, we can also see that the blue points are very tightly clustered comparing to, for example, this one, right? So they're pretty far away. So I consider that this might be an outlier. Why we don't see it as an outlier? Because we use classic limits. So classic limits are based on classical statistics like average and standard deviation, and therefore any outlier can potentially influence the position of these limits. Let me switch to robust limits, and then you can clearly see that at least this one is an outlier, right? You can see it's an outlier along the score distance. What it means? It means that it's explained at variance, it's explained at part of the data, which is not actually well in line with the other objects. Let's investigate it. So I select this, and then you can see I have 2 possibilities. I can remove it as an outlier, or I can make a plot. So let me make a plot. So this is the plot. The gray is all my data points. The red is the selected data point. You can see DRG12. And then you can see you can make this plot for Procrustes validation set or for calibration set. You can show the residuals, the explained part, and full, meaning it's the original data but pre-processed. And then you can clearly see why it's an outlier, right? So this is explained part, explained variance, and then you can see that explained part is clearly outside the rest, right? It doesn't match the behavior of the other points, so it's good to remove it. You can also see that here we have the real wave numbers and the correct title, wave number centimeters, reciprocal centimeters. This is the reason why I entered these values to make this plot looking nice. Okay. So apparently it should be removed. I remove it, and then I recreate the model again, create a new validation set, and then let me set 3 components as well, right? So again, you can see that the situation is much better, but still we have one sample which is lying far away from the rest. So I can again use robust limits, and then you can see that it also considered as an outlier. Let's check it. So I make a plot. Residuals look fine actually, but explained variance look again very different from the rest. So apparently this is a candidate for removal. So I remove this as well. Okay. Now I create a new model, validation set, and now you can see everything looks fine. Also, if I use robust limits, right? And then if I select, for example, 2 components or 3 components, in all cases, the data looks like a one single cloud of points. There is no like tight clustering like we had before. Okay, you can also see it like this. Now, if you look at the tutorial, you can see these plots. So these are the outliers that I have shown you before. You can see the normal limits, classical limits, robust limits. So actually, I just repeated everything from this figure 2 and figure 3 of the tutorial. Okay. So the next point is to find out how many components we need to use. There are several tools for that in this app as well. So you can see you have many plots. In this case, we need a plot which is called sensitivity. So we can see how sensitivity depends on the number of components. So this dashed line, it's the expected sensitivity. It matches alpha. You can see if I change alpha, it goes up. And then if I reduce alpha, it goes down. And you can also see a gray area. The gray area, it's the confidence interval for the sensitivity, because you remember that our sample is only 52 objects. So therefore, the expected sensitivity and the real sensitivity can, of course, vary because of the sampling error. And therefore, we also show the confidence interval for the sensitivity. Okay. So you can see that for the training set, all values lie within the confidence interval, but this is how it is expected. So if I look at the Procrustes validation set, the situation is different. And if I show you both, you can clearly see the difference, right? So apparently our initial selection, 3 components, was the correct one. So it's a 3 component, and then after the 3 component, you can see that the sensitivity for the validation set goes beyond the confidence interval. The second tool that helps you to identify the correct number of components is extreme plot. Extreme plot shows the number of extreme samples that were considered by model as extreme, versus the real number. So this is the expected number, this is the real number. Again, for a calibration set, regardless how many components you use, it's always within this confidence ellipse, right? But if you look at the validation set, at the Procrustes validation set, you can see with 5, you already have some points that are outside the confidence ellipse. And then with 3, they are all inside. Of course, they are all inside also with 1 and 2. So you can see with 1 and 2, and then you can see they go completely beyond, right? So this is another plot that you can use in order to identify how many components to use. And this plot also helps us to confirm that 3 components will be a good choice, okay? So 3 components, that's it. And that's actually it. So this is the model. So we can download results. I will do it in a minute. Can download model to be used in the next for the testing and for the prediction. But let me explore this model even more, right? So what else you can do? You can look at the distances. So this plot simply lets you investigate how distances differ from one object to another object. You can also see, you can show it for Procrustes validation set for both. And also you can see the difference. And sometimes difference is very good to identify outlier. For example, in this case, this difference is not very large, right? But for example, if I go back and remove some of the outliers, let me remove all outliers and make a model, you can clearly see that distances will demonstrate it. You can see the difference completely out of the, it's huge, right? So you can see the DRG12. I can actually also click on this plot and also click on this bar and also remove it, like I did in the acceptance plot. Go to distances again, and then show the difference. And then you can see, I need 3 components, you remember, right? So 3 components, and then you can see, for example, okay, 13, and especially the full distance, right? 13 is a little bit larger, okay? Especially if I use robust limits. So this is the distance plot. You just investigate different distances. You can see also if you use a full plot, it shows also this extreme boundary and the boundary for the outliers. But of course, if you use separate score and orthogonal distances, you don't see these boundaries. The degrees of freedom is essential part of SIMCA model, of DD-SIMCA model. They are computed based on the data. You can see these degrees of freedom here for the current number of components. You can see 2 here, 3 here, and 5 here. And then you can also see how these degrees of freedom depends on the number of components. In some situations, this plot also helps you to identify how many components to use. And then finally, loadings and scores are just normal loadings and scores plot like you do in PCA. There is nothing new here. If you watch the PCA video, you already know how to look at these plots. So next is these 2 widgets. You can see that this widget shows you the current model state, number of degrees of freedom for every distance, the average distance, the critical limit for the extremes, and the critical limit for outliers. If we go to distances, for example, right? Let me remove this as an outlier as well. And then you can see that this is 4. Why it's 4? Because you remember this is the f divided to f0. And in this case, f0 is the degrees of freedom. And in our case, the degrees of freedom is 7, right? So if you take, for example, these 14 divided to 7, you will get 2. So this is the limit. And if you get 28 and divide to 7, you will get almost 4. This is the almost 4 limit. Okay. So this is it. And then finally, here are the results of the classification for calibration set and Procrustes validation set. This is total number of objects. You remember we loaded 52, but we removed 2 as outliers, so therefore we have 50 objects here. Then 2 were considered as extremes. If you look at the acceptance plot, you can see these 2 are extremes, so they are rejected by the model, so they are false negatives. And then you can see 0 outliers, and this is sensitivity, which simply is 48. It's a correct number of objects. It's a number of objects correctly recognized by the model divided to 50, so that's exactly 0.96. Okay. So the next, you can also download the results. So let me download the results for calibration set. For Procrustes validation set, the result structure is the same, and the model, right? So the model object we will use in the next video for testing our model, but the result, I will show you how the results look like. So you can see this is the result object. It has some characteristics here. So first of all, the link to the application, the file name with dataset, target train, target class name. It also tells you that reference classes were provided to make these results, number of components, alpha, classical estimator, classical limits, degrees of freedom, critical limits, number of objects in total, how many in, how many out, members, regular, extreme, outliers, sensitivity. Okay. And then you can see we have also characteristics of every object. So for example, the first object, so this is a label, this is the class, this is role, regular, extreme, outlier, decision, in or out, and then these are the distances. So you can use them, for example, if you want to make the acceptance plot in Excel, and this is the full distance. So this is scaled score and orthogonal distances. And then you can see, since we removed these two, they are not present in this table. Okay. So this is it, how to train model, how to optimize number of components, detect outliers in your training set. And as I said, if you look at the tutorial, all these plots, you can see that you can reproduce all of them. You remember this one, we just looked at them, right? So all these examples that I showed in the tutorial, they can also be reproduced here. Okay. So in the next video, I'm going to talk about how to test your model.